Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. So in today's class, we are going to discuss about some numerical problems from the question bank based on the module 1. So here the module 1 is Introduction to Electrical Circuits. So in the module 1, we have already discussed what are the various elements and what are the basic properties of the electrical elements, and as well as what are the various basic laws related to the electrical circuits, so that we have discussed. So based on, and also in the module 1 we have discussed the alternating quantities also. So like, because before that we have discussed everything with respect to the DC source, and after that we have discussed with respect to the AC source, which means what are the properties of the alternating quantities, so how we can represent the alternating quantities, and what are the difference between the direct current and alternating current. So like that we have already discussed in module 1. So based on those topics, here we are going to discuss some questions from the question bank. So first let us start with the alternating quantities. So in the alternating quantities, we have discussed the various topics basically, and importantly, to find the RMS, average, peak factor and form factor of the various waveforms, because as we know, the alternating quantities are represented by the sinusoidal waveform, okay, and sometimes maybe not the pure sine wave, okay. So like, and we have also discussed various periodic waveforms in the module 1. So here we are going to discuss, so how we can find, of course already we have discussed all these things, but how you will get the questions from these topics, that here we will see, and also we will discuss the solutions for the problems presented in the question bank. So here the first question is, obtain the average value of the sinusoidal waveform shown in the figure. So first of all we have to find the sinusoidal waveform for the figure as given. So here, as we know, for the sinusoidal waveform, I mean, how we can represent the sinusoidal waveform? Here V of t is equal to Vm sine omega t, or in another words, here the omega t we can also replace with the theta. So whatever it may be here, if you get the value of these angles in terms of theta, then you can take Vm sine theta or Vm sine omega t. So as we know, the standard equation to find the average value of any periodic waveform, which is f average, or the function of the average, which is equal to 1 by t integral 0 to t into f of t into dt. So here the 1 by t, here t represents the total time period of a particular waveform, and here the 0 to t, the integral limits represent the conduction period of the cycle, right? So the total time period of a full cycle is this particular t, and the limits represent the conduction period of the particular cycle. So then f of t here represent the type of periodic waveform. So here this is the sinusoidal waveform, which means here f of t or v of t, whatever it may be. Sometimes it is v of t and sometimes we may represent with f of t. So here f of t or the v of t, which is equal to Vm sine omega t into d omega t. So because in the place of t here we are having omega t, right? Then substitute this equation, or the v of t or f of t is equal to Vm sine omega t in this equation, and simplify, okay, then you will get the average value. But before that, for the given particular waveform, we should find what is the total time period and what are the conduction periods. So here, as you can see, the total time period here it is 2 pi. So we know already how to find the total time period. The total time period is nothing but the time taken by the this cycle to complete his one full cycle is called the total time period. So which means here this is the time taken to complete one full cycle. So here this one, because after that the same cycle is repeating, right? So that's why here this is the total time taken to complete one full cycle. So which means here it is 2 pi. So that's why here the total time period, this t, is 2 pi. Then here the conduction period, as you can see, only 0 to pi, because 0 to pi you are getting some conduction, okay, you are getting waveform, but pi to 2 pi there is no conduction, so that's why here it is 0, right? So that's why here pi to 2 pi v of t is equal to 0. In another words, here this we can write like this: the f average, which is equal to here 1 by t, here it is 2 pi, into integral 0 to t, actually t is 0 to 2 pi, actual t is, but here 0 to pi there is a conduction, but pi to 2 pi there is no conduction, so that's why here let us write in two way: 0 to pi, okay, so 0 to pi, here it is sine wave, so that's why we can write Vm sine omega t into d omega t, plus then pi to 2 pi, okay, so here pi to 2 pi, which is because v of t is equal to 0, so we can make it 0, right? Then if you write this one, then 1 by 2 pi into integral 0 to pi Vm sine omega t into d omega t. So if you simplify this equation, then we can find the value of the average value of the given waveform, right? Then here see, of course, just now as I written, okay, so if you simplify just integral of the sine omega t, here it is cos theta or cos omega t with the integral of, with the limits of 0 to pi, and if you substitute these values here, then you will get V average is equal to Vm by pi. Suppose sometimes that we will see, okay, so this is how we can find the V average. The same way, if you want to find the VRMS for this particular waveform, okay, of course they didn't ask in the given problem, but suppose if they ask you find the VRMS also, then here let us consider FRMS, which is equal to 1 by t integral 0 to t into f of t whole square into dt whole to the power of 1 by 2. So again, the time period t is same and the limits also same. Only the change is here f of t whole square. Okay, which means here you will get Vm square into sine square theta and square root. So this way you can find the RMS value of the given periodic waveform. Next, coming to, yeah, here they have already written, okay, to find the RMS value also. Okay, so here the RMS value that you can find like this here, VRMS. Okay, VRMS is equal to, right? So for this particular waveform, okay, so the V average and VRMS is here, V average is equal to Vm by pi and VRMS is equal to Vm by 2. Then we can find the form factor and peak factor also, that we will see, okay, the form factor and peak factor. Then here find RMS value of a waveform shown in the figure, because here of course the difference as you can see, but here they have already given the equation for this particular waveform, which means V of t is equal to, or V of omega t, which is equal to 50 sine omega t. So 50 sine omega t. So which means actually if you compare this with the standard equation Vm sine omega t into d omega t, here also d omega t, then in the place of Vm you are getting 50. So where is there is, whenever there is a Vm, so there you can substitute the value of the 50. Again the same way here, the same way you can write here also. So here V of t is equal to Vm sine omega t, which is equal to Vm sine theta, right? So then as we know already, the average, how to find the average value. Then here the time period, yeah, here that you can see here the time period is pi, because in the previous case it was 2 pi, because as you can see here this is the time taken to complete the one full cycle, because after that again the same cycle is repeating. So that's why here the time period t is equal to pi. Then of course V average, then substitute these values, then you will get V average is equal to 2 Vm by pi. Before it was Vm by pi, here now we are getting 2 Vm by pi. Then same way you can find the RMS value, then substitute here of course the same time period and the same limits. Okay, then here you will get Vm by root 2. Vm by root 2. So this is the way to find the V average and VRMS, and again form factor and peak factor. Then find the form factor for the figure shown in below. So to find the form factor here, it is necessary to find the average and RMS values, okay, of the particular waveform. So here it is a triangular waveform. So because before in the before two cases it was sine wave, so that's why f of t is equal to what is that, f of t or v of t is equal to Vm sine omega t. But here it is not a sine wave, this is a triangular wave. So first we should find the f of t value for the given periodic waveform. So of course here the slope equation, that is 0 to what is that, pi by 2, okay, so 0 to pi by 2, because here the same way here it is 0 and here it is pi, okay, here it is 2 pi and here it is 3 pi, okay. So first of all we have considered here it is pi by 2, so 0 to pi by 2. Then v of t, you will get the 2 Vm of t by pi. So we have already discussed how to get how to find the equation for a given periodic waveform. The same way here you can find, so that we will get the v of t is equal to 2 Vm t by pi, right? So then, which means as we know the slope of the equation, okay, so y2 m into y2 minus y1 by x2 minus x1, so that is the slope. So by using that equation we can find what is that, y is equal to mx plus c. So based on that we can find the equation for the given periodic waveform. Then the same way here the time period, here it is pi by 2, okay, because after pi by 2 here it is repeating the same value. Then here V average is equal to 1 by pi by 2 into 0 to pi by 2, 2 Vmt of pi. Then if you substitute and if you simplify this, then you will get the final value V average is equal to Vm by 2. Then similarly Vrms, that you can find Vrms is equal to 1, I mean the same way, so that you will get the Vrms is equal to Vm by root 3. Then you can find the form factor and peak factor, okay, so that you will get the form factor is equal to 1.15 and the peak factor is equal to 1.73. Then for the square wave, so because these all we have already discussed, okay, then find the average value, RMS value, form factor, P factor value of the waveform shown in the figure below, right? So the same way again, right? So that's why I'm not going in detail, because here the only thing here it is two things that we should remember, okay, so that we should that we can able to identify. Then it is very easy to find the form factor, peak factor, RMS value, average value of any periodic waveform. So one thing is we have to find the equation for that particular waveform, okay, so that we have already discussed how to find the equation for a particular waveform. But anyway here according to your syllabus, here you will be having only the standard periodic waveforms, which are sinusoidal waveform, and of course again in the sinusoidal there are different types of waveforms that we have seen in the first two cases. So then the triangular wave and sawtooth waveform, okay, and trapezoidal waveform and the square waveform. So these equations we have already discussed how to find the equation for these kind of particular waveforms. So the same way here also, right? Then v of t is equal to Vm in this case, because here the slope is equal to 1, okay. Then here f average is equal to, again the same way, if you substitute the equations, then you will get V average is equal to Vm. Then similarly here Vrms also we can find, then Vrms is equal to also Vm, right? Then here the form factor and peak factor that you will get same, because form factor is equal to V maximum by V average and peak factor is equal to Vrms by V average. So in both the cases here Vm only numerator and denominator, so that's why here you are getting the form factor and peak factor is 1, right? So you may get the question like what is the form factor and peak factor of a square waveform, right? So both are 1. Or what is the average value of a square waveform, or what is the RMS value of a square waveform, that is Vm. Next now a very simple problem here, because these problems are depends on the basics of the electrical circuits, okay. Then here an electrical heater draws 3.5 amperes from a 110 volt source, then the resistance of the heating element is approximately. So here they are asking us to find, there is an electrical heater, so that electrical heater drawing a current of 3.5 amperes from a 110 volt source, because as we know the voltage is constant and the current is depends on the type of the load. So anyway here it is, let us consider a resistive load. So then the resistance of the heating element, so what is the approximate resistance of the heating element, okay, so that it can draw a current of 3.5 amperes from a source of 110 volts source. So this is very simple, which means here it is a simple Ohm's law that we can apply. So first let us write the given data. So an electrical heater draws 3.5 amperes, which means I is equal to here 3.5 amperes. Then from a 110 volt source, so which means here V is equal to 110 volts. Then find the resistance R is equal to how much? So as we know, V is equal to I into R, right? R, in another words, because here we need to find R is equal to V by I. Then here V 110 and by R 3.5. Then you will get the answer. So R, the ohms is resistance. Ohms, right? The resistance units is ohms. So this way we can find, because a simple basic law. So we know voltage and current, then we can find the resistance by using the Ohm's law. So as we know, Ohm's law is okay. So the potential difference between the 2 points is directly proportional to the current flowing through the an element or the conductor at constant temperature, right? So here in this way we can find the approximate resistance, okay, for the given heater when it is drawing a 3.5 amperes and the 110 volt supply. Next, here they ask us the question like, explain the nature of power factor in inductive and capacitive circuits, right? So first of all, we should know what is mean by the power factor. Okay, then it is easy to understand the nature of the power factor in various cases. I mean in various nature of the loads, okay, or in the various type of loads. So here the power factor, here it is nothing but the cosine angle between the voltage and current. The cosine angle between the voltage and current is the power factor, right? So then first of all we should know the angle. So usually we represent this as a phi, okay, or sometimes it is a theta also. So in other words, we can call it as the phase difference between the voltage and current, right? The phase difference between the voltage and current. So as we know here, in the alternating quantities, both voltage and currents are represented in terms of the sinusoidal waveform. But depends on the type of the load, both the current and voltage will not start at the same point, right? So in that case, we will get the phase difference. So basically, the various types of loads are, let us consider a resistive load, which means the pure resistive load, and pure inductive load, and pure capacitive load. Here I have considered the three different types of loads. So in case of pure resistive load, as you can see in the first figure, so the voltage waveform and the current waveform are starting at the same point. Of course, maybe the maximum value Vm and Im may be different, okay, but here the voltage and current are starting at the same point. So which means the phase difference between the 2 points is 0. So cos 0 is, because here as I told you, so the cosine angle between the voltage and current is the power factor. So here cos theta is the power factor, or cos phi is the power factor, right? So then here cos 0 is equal to 1. So in case of, which means the nature of the power factor in case of resistive load is unity power factor. Okay, the nature of the power factor in case of resistive load is unity power factor, and the power factor range is always in between 0 and 1. The power factor range is always in between the 0 and 1, right? Then coming to the inductive loads, okay, so in the inductive loads, as you can see, this is the voltage waveform and this is the current waveform. So the voltage waveform starting at here and the current waveform starts after the 5 degrees, right? Which means here we can say the current is lagging behind the voltage by 5 degrees. The current is lagging behind the voltage by 5 degrees, because here we are considering voltage as a reference. So here the current lags behind the voltage by 5 degrees. So that's why here we will get the power factor, okay, the angle also lagging, so that we can say the power factor also lagging power factor. Okay, so in another words here, because here V of R, so which means let us consider here it is V of t is equal to Vm sine omega t, and similarly for the current is also same, the sinusoidal waveform. So I of t is equal to here Im sine omega t, because both are starting at the same point, which are the phase difference between these 2 points is equal to 0. But here we know already Vm of t, okay, or let us consider VL of t. So VL of t is equal to here VL sine omega t, but I is after the 5 degrees, so which means here it is lagging, so that's why we usually take it as a minus sign. So IL sine omega t minus 5. Then the nature of the power factor in the inductive load is lagging power factor. Then coming to the capacitor, so as you can see here, voltage again the same way like in the previous two cases, but here the current, as you can see, it started before the 5 degrees with respect to the voltage, which means here the current is leading by 5 degrees with respect to the voltage. So which means here this is a leading power factor, and here we usually consider as the positive 5, okay, so that here IC of t is equal to IC sine omega t plus 5. So I hope everybody get understood what is mean by the power factor, okay, how to find the power factor, and what is the nature of the power factor in case of different circuits. Okay, for the capacitive circuits, the nature of the power factor is unity power factor, and in case of inductive circuits, the nature of the power factor is the lagging power factor, and in the capacitive circuits, the nature of the power factor is a leading power factor. Now derive the necessary condition for source transformation and deduce one type of source from another to the other type. So here the source transformation, which means how we can transform current source to voltage source and voltage source to current source. Of course, as we know, what are the various kinds of sources? Basically voltage and current, but in some other we can classify furthermore, like the ideal source and the practical source. Okay, so which means in case of ideal source there is no internal resistance that we usually consider, but in case of practical source we should consider the internal resistance also, which means practically every source having its own internal resistance. If it is a voltage source, then the internal resistor is connected in series with the source, and if it is a current source, then the internal resistor is connected in parallel with the current source, right? Then those are the necessary conditions, which means here the condition to transform the voltage source to current source means then the voltage source must having an internal resistance which is connected to the in series, which means let us consider a circuit. Okay, so this is the circuit, and the circuit having one resistor, like this. So V, R1, R2, R3, R4. So in this case, there is a voltage source. So is there any possibility to convert this voltage source into current source? Yes, because here this voltage source having an internal resistance in series with this voltage source, so that we can convert this current source. Then as we know, okay, so V is equal to I into R. Okay, now we are converting the voltage source into current source. So the current source I is equal to V by R. Okay, and the resistor is same. Then if I convert this voltage source into current source, then the equation, the circuit will become like this, right? So here it is I, and again here it is, this is R1, V by R1 actually. Okay, and this is R2 and R3 and R4. So the voltage source is transforming into current source. Then again vice versa, the current source can be transformed into voltage source when the current source having an internal resistance in parallel with the current source. Okay, then this way we can transform it into like this, the current source into voltage source and voltage source into current source, right? So in this case, then V is equal to here I into R1. So this is how we can transfer the voltage source into current source and current source into voltage source. So that is called as a source transformation, right? Then another problem. Household circuits in the United States commonly runs on 120 voltages of electricity. Frequently circuit breakers are installed that open a circuit if it is drawing more than the 15 amperes of the current. So what is the maximum amount of resistance that must be presented in the circuit to prevent the circuit breaker from activating? So which means here, so first of all we should understand what is the purpose of this circuit breaker. Okay, so because as we can see in every electronic appliances, so that there will be the rating. Okay, so which means, so the voltage is there and current is also they usually mention. So up to that current it can withstand. If more current is flowing through that particular circuit, then that circuit may get damaged. So to prevent that, so we usually include a circuit breaker, because as we know, whenever there is a short circuit occur in our houses, then the total wiring and some electrical appliances will damage. Why? Because high current will flow. So as we know, in the short circuit the current is maximum, in the open circuit the current is zero. So that's why, because of, to prevent damage of the electronic appliances, so here we use some circuit breaker. So which means whenever there is a high current, okay, so which means here the circuit breaker also having the capacity, which means it can withstand up to the 15 amperes according to the given problem. So if the current is more than the 15 amperes, then definitely the circuit breaker will break. So which means here a circuit breaker is nothing but like a switch. Okay, so automatically it will off, so that there is no supply, okay, to the electronic appliances, so that it will prevent to get damage. Then here, so what is the the minimum amount of the resistance that must be presented in the circuit breaker. Okay, so here again the same thing. Okay, V is equal to I into R. Okay, so here we need to find R. So R is equal to V by I. So here V is equal to again 120 by here 15. So then you will get the amount of the minimum amount of the resistance. Okay, so that must be presented in the circuit. Fine. Then a current in an incandescent lamp is 0.5 amperes. Okay, when connected to a 120 volt circuit, and 0.2 amperes when connected to 10 volt source. So does the resistance of the lamp change in these cases? Of course, definitely, because as I told you, here the resistance, I mean the lamp, okay, is the resistance is nothing but the load here, or the lamp, okay, in terms of the resistance. So when we connect when the current of 0.5 amperes and connected to 120 volts, so again as we know, V is equal to IR. So from this, R is equal to V by I. Okay, so in the first case here, V1 is equal to 120 and I1 is equal to 0.5. And in the second case, okay, so V by R again, let us consider, or V1 by R1. So R2 is equal to V2 by I2. So here V2 is equal to 10 and by 0.2. Right? Okay. So which means here this is 1200 by 5 and this is 100 by 2. Let us consider. Because 0.5 if I remove, then you will get 2. Okay. So here this is 5 2s 10 and again 20. So 5 4s and again 0. So here it is 240. Right? Then in this case R2, okay, so 2 and here it is, what is that, 50. So here it is 50 ohms. So in the both cases, the resistance of the lamp is different, because when voltage and current are different, okay, then definitely the resistance will also different, because as we know, R is equal to V by I. Right? Then explain the laws used to study the behavior of the series and parallel circuits with neat examples. Okay, so explain the laws used to study the behavior of the series and parallel circuits. So here the basic laws only again we use, okay, the series and parallel circuits. That is the Kirchhoff's voltage law and the Kirchhoff's current law, the basic laws to study the behavior of the series and parallel circuits. Which means, suppose, let us consider a series circuit. Series circuit means all the elements are connected in series. Let us consider this is a series circuit. So here it is R1, R2 and R3. Okay, let us consider here it is V. Then As we know, V1, let us consider the voltage across the, the resistor R1, and the voltage across R2 is V2, and the voltage across R3 is V3. And let us consider the current flowing through the circuit is I. Right? Then the behavior of the circuit is nothing but, so now find the total the voltage relation across the V1, V2, V3 in this circuit. So as we know, simply the KVL, Kirchhoff's voltage law, the algebraic sum of the voltage in a particular loop is equal to 0. Right? So plus minus, let us consider, and here it is plus minus and plus minus and plus minus. Then here you will get, according to KVL, V is equal to V1 plus V2 plus V3. And because the elements are connected in series, okay, so the current flowing through the series elements is same. So that's why here the current flowing through the R1 is equal to I, and R2 is equal to I, and R3 is equal to also I. But the voltage across R1, R2, R3 is different. Now coming to the parallel circuits. So which means all the elements are connected in parallel. Then here again then just connect these three resistors are in parallel. Right? So here it is V, and here it is the total current I, and here it is I1, and here it is I2, and here it is I3. So same way here R1, R2 and R3. Okay. Then here the voltage across R1. Okay. So VR1 is equal to V, and VR2 also V, and VR3 also V. So because the voltage across the parallel elements is same, because here the voltage means the potential difference between the 2 points. So here, as you can see, these all points are same, because which means the voltage as well as the voltage source as well as the three resistors are connected across the same set of points. So let us consider, here it is A and here it is B. So the voltage source and R1, R2, R3 all are connected across A and B only. So which means the potential difference A and B is same. So that is how here the voltage across each element the voltage across the elements which are connected in parallel is same, but the current is different here. So here we should apply the KCL, the Kirchhoff's current law. So according to Kirchhoff's current law, the algebraic sum of the currents at a particular node is equal to 0, or in another words, the sum of the currents entering towards the node is equal to the sum of the currents leaving from the node. So here, so that we can find I is equal to I1 plus I2 plus I3. So in the series elements, the current is same, the voltage is different, and in the parallel elements, if the elements are connected in parallel, the voltage is same, but the current is different. Okay, so this is the behavior of the series and parallel circuits. So if you will get the question like this, then you have to take 2 examples, and then you have to write the relation between the voltages and currents. So that is how we can find the laws used to study the behavior of the circuits. Here is, of course, anyway the Ohm's law is common. Okay, and in addition to that, here we need to use the Kirchhoff's voltage law and the Kirchhoff's current law, the Kirchhoff's laws, right? Then classify the types of electrical circuit elements depending on their characteristics and explain in detail. So for that, here basically the network elements are classified into various types. Okay, so which is active elements, passive elements, linear and non-linear, unilateral, bilateral, and time variant and time invariant, lamped and distributed. So these are the of course, basically the total network elements, especially in the electrical circuits, are the voltage source, current source, right, and resistor, inductor, and the capacitor, right. These are the 5 elements, okay, that we are going to use in the electrical circuits. And in these 5 elements, so based on the behavior of those elements, we can classify into these 6 different types. So first, let us come into the active elements. Again, active elements there are 2 different types. Okay, one is independent sources and dependent sources. So all the sources, all the energy producing elements are called as active elements. All the energy producing elements or energy supplying elements are called as energy supplying elements are called as active elements. So in these active elements, there are 2 different types. One is independent source, another one is the dependent source. right? So again, independence, then coming to the passive elements. So the energy consuming elements are called as a passive elements, right? So here the energy, the passive elements are inductor, capacitor, and the resistor. The energy consuming or the storing, whatever it may be, are the passive elements, right? Then coming to the again independent sources. So there are two different types, ideal and practical. The same way, in case of ideal, again voltage source and current source, and in the practical also voltage source and current source, which means when coming to the voltage source, basically there are two different types of sources, voltage and current. Okay, but in the voltage and current, again ideal independent ideal voltage source is there and independent ideal current source is there. Next, independent practical voltage source is there and independent practical current source is there, right? Then similarly here also in the dependent also, okay, so voltage dependent voltage source, current dependent voltage source, voltage dependent current source, and current dependent current source. These are the various types of the sources, right? Then coming to the linear and non-linear. Okay, so linear and non-linear is nothing but, suppose if you want to find the linear elements, okay, so the elements are, okay, obey the linearity, then we can say those are the linear elements, which means suppose if you consider the resistor, if the voltage is direct, what are the two parameters in the resistor? Okay, the voltage across the resistor or the current flowing through the resistor. So if the voltage is directly proportional to the current, okay, or these two are obey the linearity, the linear law, then we can say those are the linear elements. And other elements are the non-linear. If those elements, those who are not following the linearity, then those are the non-linear elements. Then unilateral and bilateral. Unilateral and bilateral is nothing but, okay, so in the unilateral, if an element will allow the flow of current in only in one direction, then we can say those are the unilateral. But in the both direction, then we can say bilateral. These all are we have already discussed. So which means, for best example, of course, inductor, capacitor, and resistor are the bilateral elements, but the diode is the unilateral elements, because the diode, it will conduct only the forward bias, because it will allow the flow of current only in the forward bias, which is anode to cathode. But cathode to anode, it doesn't allow. So which means only unidirectional flow. So that's why those kind of elements are the unidirectional elements, and the other elements are the bidirectional elements. Then time variant and time invariant. Okay, so again the parameters. Okay, again let us consider here the resistor, voltage, and capacitor. Okay, and the parameters of the resistor, voltage, and capacitors are the variable parameters are the voltage and current. If the voltage and current are changing with respect to the time, then we can say those are the time variant elements, and if not change with respect to the time, then unilateral elements. Okay, so like that here, based on the Marx weightage, we can write about the various or the classification of the network elements, right? And distinguish between ideal and practical energy sources. Okay, so that's what is mean by the ideal and practical energy sources. So very simple here. In case of ideal, of course, again the energy sources are two different types. One is what is the voltage source, another one is the current source. In case of ideal voltage and ideal current source, so there is no internal resistance, right? So which means here the voltage is constant with respect to, it will not change or it will not depends on any other element. Okay, so those are called as ideal. And in case of practical, so the voltage source having an internal resistance in series with it, and the current source is having the internal resistance in parallel with it. Okay, so that we can consider this is the practical energy sources. So this is the difference between the ideal and the practical energy sources. So this is all about the various or the not important, okay, the various questions from the question bank from the module 1. So in the next class, we will discuss about the next topic.
Like, share and subscribe. Hit the bell icon for more updates.